I've read 5 different system design books, Designing Data Intensive Applications, Alex Hsu's Volume 1, Volume 2, Don Martin's System Design Primer. I've done mock interviews also. And in today's video, we're going to be going over designing data intensive applications and what does all that stuff mean. So look at this. I'm just going to go through these chapters, I think, and maybe like draw on diagrams to explain them. I think that so. This chapter starts off with Klutman introducing like what is a system essentially, or like what that like data is like probably like the most important or the hardest like challenge that we have right now, and designing like something that's proper is going to be important, right? Like I mentioned like these buzzwords, so like AWS, NoSQL, it's really all about trade-offs and understanding like, you know, when to use what in what scenario. And so there's like 3 components of software. You want to make sure it's reliable, you want to make sure it's scalable, you want to make sure it's maintainable. What do these mean? I guess we'll go into the reliability, right? You want to make sure that the system does what it says and that like it's going to be consistent. If somebody asks for something, like you probably don't want it to give like random stuff. Just people aren't going to want to use an application like that, right? There's also like hardware errors and things like that, but you probably want to just prevent errors from happening ideally. And then what the current load is, latency versus response time. I don't know if this matters. Not sure if this really matters yet. Not yet, maybe in the future. And then scalability is going to be like, are we going to be able to use this to millions of users? So if we have one person who uses the website, right? Like, yeah, sure, it works for this one person. So yeah, we have one person who uses it and it works for them. What is scalability, right? Scalability is the idea that like, if one person accesses something, like, yeah, sure, it works for this one person. But like, what about for the other like 50,000 people? Will it work for them? And so it's this idea of designing a system that can handle millions of users, tens of millions of users, billions of users, and things like that, right? Like TikTok, you know, is getting up to billions. And this is probably like the hardest part, honestly, of a system design interview, as I kind of mentioned before, is that like reliability, like this is, you know, kind of the object-oriented programming, it feels like the approach where you just want like to make sure that you want to write good tests. You want to make sure that like there's like systems in place that when somebody like actually does something, you can roll back. But scalability is like the hard thing because there's a lot of problems when it comes to when you need to build out several servers. For most startups, it's just like, hey, like do reliability and then do maintainability. Let's maintainability being like the idea that we can evolve our code over time and that it's not going to be like a massive hassle of like spaghetti code where you make a feature and then it breaks other things, right? We want it to where this is like long lasting ideally. And this is the kind of 3 tenets of this book. Although I think it's mostly focused on scalability because this is just like it's just a much harder thing to actually do, right? There's a lot of books on how to write good tests and things like that. And a lot of LinkedIn gurus talking about all this stuff because this is like the low-hanging fruit in my opinion. But okay, cool. So let's go into number 2, right? So how do we store data? This is going to be like the biggest thing, right? What database do we want to use? Do we want to use a database at all? And if you read in chapter 2, like this is what he's going over. So we have like relational databases versus document-based SQL databases, right? How are you going to know? What are the pros and cons of them? How do you know which one to use? The TLDR is that you want to use relational when I feel like for ACID properties. So like when you have data that you really want to make sure is like correct. And if you have like complex joins and things like that. And then for the document model or like NoSQL type of models, like helps with like scalability or like if you just don't have like those problems. Yeah. So we'll say like one-to-many, JSON is hard, a document model. These are just like more historical stuff, I think. Schema flexibility, right? Don't need to enforce stuff. Relational has a schemas, like the schemas really matter. You can't be flexible. Data locality, query languages. I've heard that like graph databases don't even like matter apparently. Like a graph database is just like a NoSQL database, but it just has like fancier like syntax that you can use. And let's see, property graph model. Like again, I don't think these are like super relevant. I don't really hear them talked about, and I also don't see them like really designed that much. Oh, also another thing that I want to talk about. All right, so like another interesting thing about system design is that it's way more like biology, and that like you can actually just learn it by just watching lectures or like just reading books. Unlike like theory is like a lot nicer versus system design than like data structure and algorithms, which is like math or physics where you have to practice solving problems in order to get better. But yeah, that's something I just want to bring up. So here we've got like, you know, chapter 3, which I guess is deeper into actually storing the data. What are ways that we can actually store them? We talk about SQL and NoSQL, but like, what is that? What even is that? What is it underneath, like, you know, that hood of it? And so here we get into these like actual methods. So we've got like, oh, well, we can just store data as a file. So we, you know, literally pop open a TXT file And then we just like start writing records like, oh, this happened, this happened, this happened. But then like what happens if we want like a backup? What happens if we want to like search for something individually? Well, now we've got to search the entire file, and that's like an O of N operation, obviously, right? And these are slow. So how can we do better? And we've got like write ahead logs, which is where we keep track of the offset, and then we just write based off of that, right? So this is like version 2. Where we write, but then we're like, oh, well, I want to go to this offset. And now we can actually immediately go there in like O of 1, right? And we can write. Like, you know, like when I'm talking about these write ahead logs, like you kind of just have to know this stuff. And this is something that you don't really see a lot for DSA. Yeah. Like if you just study your notes, you take notes on it, you study, you read the notes, like you'll be fine probably. But you should do mock interviews for sure. I mean, that's really gonna seal the deal in, because there's a lot of nuance. A lot of nuance in the interviews, where sometimes an interviewer wants you to talk about write ahead logs, but the other times they don't want you to. And then this is what SS tables and LSM trees, this is how NoSQL databases typically work. Not all NoSQL, right? Depends. NoSQL is pretty flexible, but this is how Cassandra works. It's a pretty famous thing, which is using SS table. What is an SS table? I also don't really know. I just know it's good for writes, honestly. That's it in these notes. It probably explains it. I don't know. And then we've got B trees, which are good for reads. And this is what MySQL uses, a B tree. And it's also what DynamoDB uses. But it's, you know, it depends, right? We get write heavy requests. We got good reads requests, B trees, right? And then we get other data structures too. And then we also have analytic databases. So if you have to like run queries on things multiple times, right? That's another type of database that you're probably going to want. So, you know, somebody designed something that was like really good at storing for queries. So instead of like let's say you want to get all, you know, people in the United States. Well, you would just like store that data into the table, into the row, so that you can just query that repeatedly. Or I guess it's what I think they're called column-based tables. So you can have over 100 columns. I guess it's somewhere in the book that I don't have written here, but essentially instead of querying rows, like, you know, like you would normally do, you can just store all the queries like pre-computed and just store that data like as its own kind of row, so to speak. And then you don't have to check every single row like you normally, or every single column. You don't have to check every single column to see like, oh, who's from the United States and who has like this thing. That's probably like a really bad explanation, honestly. I need to actually study back up on that. But okay, this is like the first like chapters 1 through 3. So we did this in 15 minutes. Now we're going to go into like more advanced stuff. Okay, so the first chapter of designing data intensive applications is going over reliability. Like what is like a system? What is a good application? How do we know what that is, right? And he boils it down to 3 concepts, which is reliability, scalability, maintainability, right? Reliability is this idea that if your program throws an error, it's going to be like some kind of consistent error that like users are going to know what is wrong, right? Like if somebody like tries to send money to their friend, that if it throws an error, right? Like one, it shouldn't really even throwing errors, but if it does throw an error, that they can at least know that, and that the system isn't just going to completely die because of, you know, that one case. Number 2 is scalability, right? So it's, okay, sure, your program works for one person, but can it work for 1 million people at the same time, right? And then maintainability is the idea of like, can it evolve over time? Is it, if you make a change to it, is there like a ton of spaghetti code and you fix one thing and then it breaks everything else, right? So that's chapter 1. And in my opinion, I think that, I think that like, you know, this is like probably the core part of his book, is the scalability, because this is like, you know, again, we talk about a lot about reliability, which I misspelled, and maintainability, which I also misspelled. And the core thing is also I misspelled scalability. Bro, what happened here? Did I scale ability? Maybe I didn't actually, I don't know, scale. But yeah, the hard part is like doing this is like everybody already talks about this stuff, like, you know, test driven development and all that, but nobody really talks about scalability. So most people also don't really need to know about it. So that's probably the reason. So then we go into when should you use SQL, NoSQL, and I guess just briefly going over this, it's going to be use SQL when you want like ACID or like really strict parameters. ACID, you know, being like that consistent things happen, that like there's no like dirty reads or dirty writes or things like that, where people are like reading data they're not supposed to be reading, or like race conditions and things like that. Like for example, for like a banking application where somebody like accidentally loses $1,000 just because the system was, or the database like, you know, had a hiccup. And then graph models, and okay, how do you actually store the data? So the third chapter is like, okay, we talk about like the pros and cons of NoSQL and SQL, but like what actually is that inside the data. And what you'll notice here is that like, okay, so the base thing is just like, we just store it as a TXT file, right? Now, the problem is that that doesn't really scale. If we've got a lot of data, we're doing like an O of N thing whenever we do want to look up some specific type of data, right? If we want to know what was said here, well, now we got to go through the entire thing. And that's like very expensive. And it's just not going to work on like large scale applications where we've got lots of text files. So the next level of that is that you can have a write ahead log, right? So we can say a wall, which is that we write the data every single time it gets appended to the end, but we also keep track of the offsets so that now we can like, if we know like this one is located at like index 2 or something, we can actually just jump to index 2 directly and read it. So now it's like O of 1 if we know like what the offset is or off like of that data. And this is nice. This is, you'll see this in like message queues and stuff, although I don't think he mentions it in his book at this point. And there's things like, okay, so what do you do if it needs to be recovered, right? What happens if like the server crashes and it was writing and like, you know, it broke? Well, you can have copies, right? You can take snapshots. You can keep track of every single thing that you've written in like a very long log. And then when you go there, you say, oh, well, let's just redo everything up to like our, you know, our endpoint or whatever. And then, right. So appending is fast, crash recovery simple, removing old segments, removes need. And then hash table must fit in memory, and then range queries are difficult, right? So range queries is like, what if we want to, so it's O of 1 for one entry, but like, what if we want multiple? And we have to kind of like jump the needle several times, I think, to actually retrieve that, which is expensive. Cool. So then we move into the SS tables and LSM trees. Now, again, I don't remember this fully. I truly don't remember it, but I just know that these are slow at reading. I think because they have to write multiple copies of data or something, but I just know that they're slow when it comes to reads. And then B trees are good for reads. And this is what a SQL database uses, a B tree. So instead of having like this file like this, we can create some kind of tree structure, store files. Why am I doing arrows? Store files like this. And then when we want to retrieve them, now it's like login, right? Look at that. Log in. What other structures, right? So like there's other things. Actually, these are really the core. I'm sure there's like other ones like primary keys, and I guess there's stuff like here. And there's also column-based indices, which is another thing I wanted to talk about. Oh, and then there's also full text search thing. So Elasticsearch. So there's another idea too, where you can have like if you want to like search for text, like let's say we've got like Twitter and we've got like a ton of files or whatever. What you can do is you can use an inverted, I think it's called an inverted tree. I don't remember. But essentially the way it works is that you say like, oh, well, if I'm looking for cat is going to be in document 1, is going to be in document 2, and like document 3. And so that whenever we want to know like, oh, what are all like the documents that contain cat, we can just like, you know, pull that up essentially from there. And you do that for like cat or like hat, you know, maybe that's like doc 0 or something. But this is a faster way of like, if we want to like parse and search something. So like the man, like the man or something. We want to search all tweets that say the man. Well, we can just kind of go through our tree and then it'll like tell us like what things have like, you know, all these words. But this is Elasticsearch, which is again, very popular kind of service for like this full text searching thing. But again, I don't think he mentioned it in here, but just something. Second thing here too, is we got, so analytics type of databases. And again, I think analytics is essentially the same. It's just like, so it says data warehouse is typically a relational database for queries, and then one central table that branches off into dimension tables. And I might be wrong here. Maybe this is something I should look up, but like, I think that when you have you have like a typical database or whatever, which is just like this, you've got like your rows, right? These are all going to be every single entry, and you got like your columns right here. And then typically if you want to do a query, like you'll check every single row, which is like, you know, kind of big, right? It's like, I mean, that's probably O of N for like every, you know, N being like all the rows that you have. But what you can do is just store those queries as their own column. So then you take all of these and you say like, oh, well, maybe like these are like US people or something. I think this is the idea. And then you just kind of like store them. I think these are called column-based databases, although I should probably spin that up. But essentially the idea is just you can speed up your analytics queries. So like if you want, oh, I want someone from USA. I want the person from India. I want the people from, you know, like Russia or something. Instead of constantly doing like this O of N thing, when you want to run this like, you know, 1,000,000 times, you can just like pre-compute it essentially, and then just like store the result of whatever it is. And I believe that's how it works. It's my understanding of it. Okay, cool. So that is that, chapters 1 through 3 of DDIA. Let's go into the next one. Cool. And the cool thing about this is that I actually kind of read this one pretty recently. So Chapter 4 is encoding and evolution. So one, we kind of talk about maintainability, and this is what he talks about a bit here with evolution, which is the idea that like when we make a change to the code, right, it's not going to break stuff in the future. And the other bigger thing is just encoding. Honestly, this chapter doesn't feel like very, very important when it comes to system design, but it's kind of useful, I guess, knowing like how computers are even doing stuff. So with encoding, he's talking about this idea that like when you're coding something in Python or C++, the data object that you use kind of change and modify, right? Like you can have like some service that's doing this, but then you have to send it to another service that's using like Java, right? Maybe we have some application that has like some array, right, in C++, or it has like some, some dictionary in Python, right? But you have to convert that to Java. And this process is called like encoding. This is the encoding. And this is going to allow us to send data to multiple places. And so we could even do that. We could even do it for what else is it? We can even do it for like another service, like some other like microservice. I don't know. But it's just the idea that like we're like, kind of change. And how that works is there's multiple ways of encoding, right? So there's like JSON. This is like the most common, I think. JSON. And there's also multiple pathways of doing it. So there's like HTTP requests of like sending the actual data. There's HTTP. There is like message queues. And then there's like gRPC. These are how we're going to be sending the data to like other services. And then in this method, we can send it using JSON, XML, or like pure binary, right? And this is how like this kind of process is working when you actually have like C++ code and you want to send it to servers, or you have JavaScript, you have a JavaScript web application and you want to send it to the server or something, right? You encode it and change the data type to what it's going to match. So instead of just Java, right, we're sending it to like a DB, send the data to the DB. And then we have encoding and serialization. This is actually a Leetcode problem too, like a little bit, but probably much difficult. And then we can encode it into bytes, right? So kind of what I was talking about is that you have pickle, serializable. And if you do that, I guess you're tied to one language. And you have to decode like bytes, which people can sneak in like malicious code into the bytes that'll just be read like straight up. And then there's no versioning for these libraries. So we get JSON, XML, and binary variants. So we get XML, JSON, CSVs. These are way that people like typically store data. There's a lot of complaints for like each one, but there's not really any other idea, I guess, is what Kleppmann says in his book. And yeah, specifically, I mean, he brings it like some specific problems, which is like there's ambiguity around the encoding. I guess you can't distinguish between ints and floating points. You lose accuracy with large numbers. Yeah, but generally just good. It's generally good enough. And then we have binary stuff. So it's going to be fast, which is going to be a good benefit. Send the data fast. BSON, BJSON, BISON, SMILE. This stuff, I don't care a lot of too much stuff. So he talks about, how it actually works under the hood. I don't think this is relevant for a system design interview. I don't think that any questions really ask you about this kind of stuff. So I would just skip it. But if you're curious about like how these binary encoding libraries work and like how they can, take a byte and like store it, he talks about like you can create like these structures or whatever. And so we have the data flows like HTTPS, RPC, message queues, right? Database calls. And for HTTP calls, we have REST versus SOAP, remote procedure calls. Not really sure why they use them, but apparently it feels like it's just another way. I don't know. Feels like it's just another thing. I like truly have no idea why you would use RPC over HTTPS. Most of the time, I think it's just HTTP. That's how you send data between things, and then message queues. But anyways, that's the encoding section. I don't, it's not really a whole lot. But just kind of interesting seeing how like, okay, how do you actually send data between a database? How do you send it from like your Python to your database, and to your, Python to your server and things like that? It's just kind of all like this stuff. So yeah, replication. So like, how do you prevent stuff from happening to where you have this system, but you don't want to like lose the data permanently? I believe that's the question that replication's asking. There's also like, it also helps with scalability. If you have like too high of like a server load, you can, offset it. So one of the first things that Kleppmann will mention in his chapter is this idea of leader follower, right? Which is that you have one leader and then it's going to send that data to the followers. And so if the leader actually fails, the data isn't lost because there's actually copies of it. And leader follower is also nice too, because if you have like a ton of read requests, they can actually just read from these other servers that you have, from these servers down here, which are the followers. So your only bottleneck is just like your write throughput, which I'm not sure what the number is. I think it might be like maybe like 20,000 writes per second. I'm not sure how fast a DB can write, but so let me make sure this is correct. Replication is useful for when one system goes down, all the other ones are still going to work. And then the data's not going to change over time, right? So one, you don't get a single point of failure. And like, I mean, I guess it's useful if your data is not constantly changing. Although I feel like if your data is changing, it's kind of fine. I'm guessing this means like write heavy type stuff, which is what I'm talking about here, maybe. I don't know, actually. So distributed databases must handle the challenge of data changing over time. So we've got like 3 different strategies: single leader, multi-leader, leaderless, which have like just a lot of problems. Leaders and followers, right? I kind of talked about this. And there's synchronous versus async. You probably want async, would be my guess. And then you can add new followers, but you probably have to just make a snapshot and turn it off if you want to add something new, right? So like if you want to add a new one, your system's already like set up. Well, you're probably either gonna have to stop it briefly and just turn off the system, or I guess you take a snapshot and then just like write over and then have it like follow up whatever the snapshot was. And so this node clones whatever the snapshot was. They get node outages. What are you gonna do if one of these nodes crashes and dies, right? Well, now you have to make a new one. And how are you gonna make a new one? Right, again, we keep a log of all the changes and then you restart it and then just have it read the log. And if the leader fails, well, then this is a bigger issue because now we're no longer getting reads. And we also have to handle like this idea of like swapping. So like if this one crashes, we have to like place this other one here. And again, this is like this kind of stuff that I'm talking about is like way beyond like a mid-level engineer. This idea of like swapping nodes, I don't think that will ever be asked you in an interview, but you have to replace the node. And then you have to hope that you didn't lose any requests or that the requests are still like in the log or something. And then the same thing too with split brain where 2 nodes think they're the leader. So yeah, like I said, I think this is out of scope for a mid-level, but you know, just kind of something that you can know is that like, what do you do if a node fails? Probably not going to get asked it, but what do you do, right? You have to like, okay, kill it. You're going to have some replication log that goes up. And then what do you do if it's like a split brain where this node died temporarily because it failed like the heartbeat checks? And then we swapped this one here, but then we actually kind of messed up because this one was still alive. And so now we've got like 2 things that are like, you know, getting like information. Like that's a problem with this kind of system is that you have to handle this stuff when you're trying to implement this on your own. It's very annoying. This is why, you know, we have cloud like AWS cloud, because it already like, it just wipes away all of that stuff. But this is why it's so popular, because this is an annoying thing to have to code for scalability. Okay, implementing replication logs, write ahead logs, logical logs, sure. Replication lag, we can just wait. So it's not always going to like catch up immediately. There's always a delay when you're sending data to something. Always some delay, especially when it's over a network. And then sometimes like things just get lost. So sometimes you'll have like messages that are just like gone, unless you're doing like a message queue maybe, but then you're just gonna have delays if you're using a message queue. So now you're introducing delays. So then you just wait, eventual consistency, just wait. Reading writes, monotonic reads, consistent prefix. I don't know any of this stuff. Probably not gonna bother with that. Multi-leader, you can have multiple leaders, right? So if you have some multiple data centers or you want to reduce latency, this will allow you to have multiple or higher throughput. So you can actually record, you know, multiple types of things. Yeah, now you can have like multiple, you know, kind of throughputs. Instead of like 20,000 per second, you can actually go to 40,000. And then if you start sharding, that can help too. And then we have leaderless replication. Leaderless is supposed to be like easier when it comes to distributed system because it handles by consensus. Apparently DynamoDB, Cassandra use this. Yeah, this is the idea of replication. There's also like, if you want like an easier kind of thing, right? Obviously there's Don Martin's where if you go over his replication, it's like master slave and then master master. And where does he have this at? Yeah, like his is just like 1 page, right? So like notice how I spent like kind of 10 minutes just talking about this stuff. But like his is like, you know, 2 paragraphs, right? This is what I'm talking about. This is what I mean when I say like depth, is that DDIA goes way more in depth. Although you don't need to know this stuff. Nobody's probably going to test you on the fact that like, what do you do when a node fails? And like, how do you have a replication log? But like, you can just go through and just say like, what are pros and cons? And then federation. With that, let's go into chapter 6. Although, I don't know this Don Martin, so maybe I should just look at it. Leader follower, additional logic needs to promote a slave to a master, and then disadvantages, replication, but it's the same for both, right? I think replication is just going to be slow, probably. Data loss, writes are replayed, A lot of writes, read replicas can get bogged down, requires additional hardware and complexity. Disadvantage of master, need a load balancer. The thing is further reading and stuff, but yeah. Chapter 6 is related to partitions, and the idea behind partitions is that like you can have a database, you can have like some database, that has like some entries or whatever, but you can query things way faster. Again, we don't have to do O of N. We don't have to go O of N. Oh my God. We don't have to go O of N, like searching everything. We can actually just group them based off some kind of criteria and like split it. So like maybe A through Z or A through, A to C is here. And then we have another one that's like, D to F or whatever, et cetera, et cetera. And so now whenever we want to search for A, it's actually like a lot faster than O of N because we don't have to search everything. Not everything is like jumbled. So that's the idea behind partitioning, is that you can increase speed. And in some cases, you can have like entire databases that are just dedicated to like the letter A. Nice. I love it. Some databases that are like dedicated to like the letter A or something. Just chill. Cool. So there's also the issue of like hot partitioning. So like this A, B, and C thing it's not practical because maybe you can have like A's that are taking over. And so it ends up being bigger. It's not like evenly distributed. But I think this is where the hash ring comes in. But okay, sharding. So it allows you to break up data into partitions where each partition is essentially a small database. You can distribute a large data set across many processors, leading to faster lookup times, right? We're not hitting O of N anymore. We're hitting like probably login or even probably login, I guess is what it is, but it's much faster. So we can do key range partitions, just group them, right? You can have some hotspots though. And this is another issue where, again, out of scope for mid-level, I think, or at least maybe for like a low bar mid-level, but you can have like hot keys, and then you need to figure out a way to handle that. So you can have a hash function, right? Just consistent hashing. And then we have here, we can have secondary indices, right? You can also, indexing is like a thing, but you can also have secondary indices, and you can also have like sorting keys and databases. But again, this is like out of scope. You can have multiple like indices. And then rebalancing partitions. I just did not go through this that much, but I guess look up consistent hashing if you're curious about this, curious about that kind of stuff. Okay, cool. Now we're back to the stuff that I kind of like studied more recently. I should probably go through the partitions again, but I don't know how much I want to do that. Anyways, we're going to end this chapter here. I think maybe we can even look at the Don Martin thing too, actually, while we're at it. Partitions. No? Where's my partitions? Partition tables. It's like literally like nothing. Yeah, there's just nothing on partitioning. Anyways, yeah, that's all you would really need to know. So I think so. That's about all you would need to know. I don't think you're going to ask anything more complex than that in a mid-level interview. Cool. So these other chapters are, I believe, like they're higher than mid-level. So you don't really have to like know about this stuff. But if you're kind of curious, I think it's, it's good to know probably. But we'll continue over with chapter 7. So transactions. So this entire one is, I believe it has to deal with like preventing race conditions and preventing like dirty reads, that you essentially have like multiple states of your database. Like what if you have like a database, and what if you have a database and you've got like all these entries or whatever. You've got like a query, you got like one query that's going here to here to here to here, and it's like changing stuff. So like now the stuff is like dirty, and then you have like another one that's going like here, here, here. Well, like now your thing is like, now your system is like kind of screwed up. So like how do databases prevent that? And like what are algorithms and strategies that they can use to prevent things? Obviously like a lock is like, a deep one. So you just lock it. So you say nobody can access it, and then they just have to wait. But that's very time consuming, and your system will have like worse performance if you're doing that. So like what ways can we fix this, right? Many things can go wrong, right? We can have hardware that fails. So you were writing something and then it fails, and so it never fixed. And so now you got to like roll back things. I just mentioned you can write to the database at the same time. And, in order to be reliable, they have to deal with this. So a transaction is just like a unit of several reads and writes like grouped together. So it succeeds, you commit, or you fail, right? And there is the like all databases support transactions. It's pretty acid. One thing that Kleppmann mentions is that acid isn't even like defined that well. Like consistent means like absolutely nothing. Consistency means like absolutely nothing. It's not even like actually, there's no metrics for it. It's just kind of like this word people throw out to sell things. Basically, it's just like, oh, it's consistent. Oh, this is eventually consistent. But like, what does that even mean? Like, it means that like, yeah, it'll eventually catch up. But like, is there any time limits, right? There's a big range of numbers that you can kind of get through. And yeah, even more vague than ACID. So we have base. This is what NoSQL does. So they say like, oh, it's basically available. It's soft state. It's eventually like, what does basically available mean? Can you give me like actual numbers on it? Nope. Okay, so like what is ACID? We go through every single thing. Kleppmann goes through every single thing, which is atomicity. You can have one thread that executes like the operation. There's no half states. We have consistency, and which is generally that like everything's eventually going to kind of catch up to the same data, I believe. And see here, if a transaction starts with a valid database according to those invariants. And then isolation, so just no race conditions, no half states, no race conditions. The data eventually like catches up, right? Nothing's going to be like kind of inconsistent. And then durability, right? So that it's going to be persistent, that it's not going to crash or get corrupted or whatever. Like ideally it's going to like have little, but there is no perfect durability because things can get, power outages can happen, disks wear away. Yeah. Cool statistic. One study found that 30 to 80% of SSDs develop at least one bad block during 4 years of operation. Okay, cool. So there are single object transactions where you have multiple reads and writes on a single row of a database. And then you can have multiple ones where you want to write to multiple rows, essentially multiple objects, which I guess it's called. And then we have handling errors. A key feature of transactions is that it can be aborted. Weak isolation levels, concurrency bugs are hard to find by testing. Serializable operation. Like, I guess this one's kind of interesting, right? So there are different levels to isolation, and it doesn't just go like at the strongest level of like, oh, this will never ever happen. Because again, there's the performance trade-offs, right? Like we don't want to just lock this thing and just say, oh, well, yeah, just nobody can use it until I'm finished. There are ones where you can just allow multiple reads, for example, and you can say everybody can just allow to read this one. And this is like the lowest level, and you can set these in a database. So if you have like a MySQL database, you can actually just say like, oh, I'm okay like doing this at like, you know, like the read like level or something, like read, you know, other things can read or whatever. You can have like the read lock or the write onlys or whatever. So serializable isolation, and then right, it's like preventing performance costs. You use like the weaker isolation level. You can have concurrency bugs, but it's not always needed to have like, oh, let's just be strongly consistent or whatever. You can have like serializable where you have to do every transaction has to go. But you can have like some applications or even a lot of applications where that doesn't matter at all. I guess like one application, if I were to give an example of one, is like maybe like Facebook, like messages maybe, where you don't really care if a post is like, has like some kind of bug in it because nobody's like going to die really. And especially if it means your page loads faster. But yeah, I think most people would just say like, oh, it needs to be like perfect. You should never have any bugs. Okay, this is it. Read committed. Okay, read committed. That's the first one. Only see the committed data. No dirty reads. And when writing, overwrite data that has been committed. No dirty writes. So like if something is modifying this row and something else reads it, right? You should only read it when this first one finished. You can still read it, but like this one just needs to be like finished and committed. And then dirty writes is the same idea, right? Like if something is writing this, we don't want to allow reading. It took me 3 to 4 hours just to type the notes on this one. And I'm kind of going through it pretty fast. This one took me 3 hours, I think 3 to 4 hours just writing out this, reading it and writing it out. How do you even implement something like this? So he goes into how you implement it, which I believe is like versioning. I want to say you use row level locks. When a transaction wants to modify, you just lock it. Right. And the problem is that like if one thing locks it for a read, well, we still want to like allow reads. And so what we can do is we can version this and we can say, oh, if it's locked, just, hey, check out the old version. Oh, this is locked. Okay. And then go to the old version of it. And then you return that data. And so now things can go fast. Now things can go faster. Now there is some problems with this. So you could have someone who transfers money to another person. He talks to this Alice and Bob example, where Alice transfers money to someone. I wish I had the diagram, but I guess I don't have it. I believe it was that like Alice transfers money to someone. So she's like negative like $50 and that person is like positive $50. But there's like a brief moment where this person looks at what her account balance is. And then it says that she has like $50 because like the transaction never finished, which would be like really confusing for that person. And he calls this like a non-repeatable read or a read skew, just for a brief second though. Implementing this stuff, transaction levels, like this is a lot of stuff to memorize. Transaction, ACID, Atomicity, consistency, durability. This is a lot. But there's like which is like the reason why most people won't read any of this stuff, and probably most people won't even watch this video that I'm making. But for the people who actually want to learn stuff, I do want to like kind of give this as a kind of like an option. But yeah, I mean like Bjerkson, this is like this is the hardest kind of concept that if you can learn this thing that is like you're saying like it's very easy, but if you can learn this, bro, you're making $1 million a year easily for sure. $1 million a year if you can know this information. And like put it into practice, of course. But like, because what's going to happen during a system design interview is, yeah, sure, you can draw the boxes, but what they're going to do is they're going to ask you, oh, okay, so like, well, one, they're going to say like one question they could ask is, oh, like what isolation level do you think we should have? Like those are like things that they can ask, and why? Like why should we have this isolation level for this application? Cap theorem, yeah, cap theorem. Okay, snapshot isolation is the most common solution to this problem. So each transaction reads from a consistent snapshot of the DB. Typically use write locks to prevent dirty writes. Database, multi-version concurrency control, repeatable read and naming confusion. Calls it repeatable read, something call it this, right? Like, yeah, this idea of repeatable read is different depending on like what database you're using. Preventing lost updates, atomic writes, cursor stability. Make an exclusive lock that blocks reads until the update is finished. I think this is fine. This like makes sense. And then replicated databases are like even more annoying because now you have to do this and worry about like different nodes having different types of data. There is another one too with compare and set. Yeah, there's another issue too with compare and set, I think. So like here's like, this is like one issue. And then the other one is that like you can have multiple doctors that need to be like on call or something. And you always need to have one doctor on call. And then if like two of them try to do it at the same time, then it like doesn't work. So you need a compare and set before you do that. So like you can have like, two people who want to like leave, but you need to have at least one, but then you execute the first one and then you execute the second one, but you never check to see if it was 0 before you did that. And this one like should never happen. And so now you've got like doctors that think that they can leave, but they actually shouldn't. So this is the compare and set idea. Okay, and then there's another problem, which is the write skew and phantoms. Oh yeah, so this is what I just talked about, which is write skew and phantoms. If two doctors check out at the same time, a condition can occur. Right, the snapshot will say that both are because there's like just no check. Characters and write skew, lost update. More examples, you can have meeting rooms where two people book the same room, but they weren't supposed to. Two people who have the same username in a video game and they try to like claim it. I feel like this is just really difficult. TLDR, this is really difficult. I know this is like, again, I was like, y'all keep saying this. This is above like mid-level stuff and I'm not going to bother with it, but fixing this seems like it's a difficult problem. Okay, serializability. So we're almost done with this. This is going to be the hardest, the strongest type of isolation level. It's going to also be the slowest, right? Strongest isolation level. It's going to be the slowest. So we just execute transactions in the order that they come in. And then we can also do two-phase locking and maybe some optimistic locking type of control. So like versioning, essentially. And then actual serial execution, right? The simplest way is we just do one action at a time. It's just slow to do it that way though. So when we mean one transaction at a time, right, we've got like all these things that we want to do. So like one, let's say we want to do like, XYZ. And then two, we want to do this one. We just keep the order of them and then just like do this one first and then do the other one and so on and so on. Database can't just sit around waiting for users to make up their minds. If they want to book an airline ticket, transactions are broken up. Application must submit the entire as a stored procedure. Database is much more performance sensitive, no version controls, stored procedures, partitioning, and then two-phase locking, which is an algorithm for getting this serializability. And I think it seems like it's defined off this. When someone wants to write to an object, you need the access. If transaction A is being read, then B has to wait for A to finish. If transaction A is writing, then B needs to wait until A finishes. So you're blocking the readers and the writers. So there are several databases that are using this, and it's called two-phase locking because when locks are required, the second phase is when the transaction executes. So the permaface is very slow, and it's very easy to have a queue of transactions that you need to run. And I believe that's it. Serializable snapshot isolation. So then I think this one's just like versioning, but instead of pessimistic locking, we just do versioning. So that's transactions. The TLDR of this, this chapter, again, it was like really long. It took me like 4 hours probably to go through, but just want to know that ACID is a thing and that there are different levels of isolation, that even with ACID, there's like different levels of ACID. You have this thing called base, which which is basically available soft state, right? Just very vague. But there are algorithms and things that we can use and set different types of levels depending on like how disastrous it would be if we had like, you know, an inconsistency in the database or something like, you know, overreading over something, essentially. Never seen locking like this common during a system design. Locking? I mean, locking comes in for sure. It comes in, it's a very popular one. If somebody gives you like if someone asked you to design a booking system, for sure it would happen. So like airline ticket, you know who I kind of like is all this Hello interview people. They've actually done a good job with their social media. They put out some helpful content, but Ticketmaster, like you're probably going to see that. I haven't read this article, like, and I don't remember it really, but I'm pretty sure they're talking about locking here just because this is something like you need to be able to lock things. And so, you know, I don't know, the pessimistic locking, right? Like, oh, you just wait. This is like the thing that everyone would think, oh, just lock it and wait. But there's other things you can do. Then again, these people aren't going over every solution, but like you've got ideas. And then, you know, obviously, but like Ticketmaster, there's inventory systems. Not really. What's the other one? Hotel booking systems. Like these reservation applications, they're using this locking type of idea. So yeah, so that's transactions. That's why we're, you know, kind of go over this stuff. It applies over to some other systems.